what we did is getting some more intense programming stuff. Surprise! We started by learning how to declare variables. Specifically, we're declaring an integer with this intx. We then discussed the use of increment operators, which are used in both finite and infinite loops. We'll talk about finite loops later today. But in this case, we're using an x operator to increase this x value by 1 each time the void draw function loops. Remember, the void draw function goes over and over and over and over and over and over again until we stop it. So you haven't missed anything if you're just now coming in. I'm just going over a quick review of what we did last class and just talking about variables and increment operators. Very important we realize what these increment operators do. So we then saw what was happening when we ran this code, which was a circle is just starting to go against the screen, or across the screen rather, leaving this cool little trail behind it. We learned how to fix that trail by actually declaring our background color within the void draw loop, so that every time this loop reiterates, the background will be redrawn and get rid of that annoying tail. So let me see where we are. We talked about text. So text being a string. Strings are denoted by things that are in quotation marks. And we determined where the text would start. Its x and y value correspond to the top left of the text. So we can also change the text size. We have to do that before we worry about the text if we want to do that. And what's up, Gavin? Do you have a question? You lost connection and now all the chats are gone? Alright, well, I think I can just... Is this it? Yeah, here we go. I sent it to you in a private message this time around. So hopefully you can see it there. So there we go. We talked about print line, which doesn't do anything inside your GUI window, but it does show you values in the console, which is at the bottom of your processing window. And we also discussed how we would use increment operators to go in increments greater than 1. In this case, we declared some extra variables, and within our void draw loop, we added this x equals x plus speed. So again, how this x equals x plus speed works, each time this iterates, it's going to take the x from the previous iteration. So the very first time it runs, the x value is going to be 0, as we declared up here. It's going to add it to the speed, which is 5, and create our new x variable for this iteration. So this new x, which will be 5 if we add 0, which you can find here, plus speed, which is 5, will be replaced. We'll be replacing the x and y values in our text and our ellipse, so we can actually see the ellipse going across the screen and our text go diagonal across the screen. So the second time it iterates, it's going to use the x from the first iteration, which was 5, add speed to it, and create a new x, which is 10. And it's going to go on into infinity until we stop it. So right now, you don't have to open any projects. We are going to be working on a new project today. So don't worry about opening a project. I just want you to have processing open. We finished off class by adding a couple of if statements. So if statements basically say, if a condition is met, if a condition is true, something within these brackets is going to happen. Anything that you tell the computer to do within these brackets will happen. So what we have here is saying if the value of x is greater than the width of the screen, which is determined up in the size declaration. If x is greater than this number, we're going to multiply our speed operator by -1. So it's going to make it appear like the ellipse is bouncing off the right-hand side of your screen. We also had to do the same thing for the left side of the screen. So we're saying if x is less than 0, we're going to reverse the direction of which the ellipse is going again. So here's what we had. This is what we had created. So ignore that this is a circle, but notice that the ball is bouncing back and forth, as is the circle, but the circle is going, or sorry, as is the text, but the text is a little bit different just in how we declared it. So this is what we ended up with last class. Any questions on what we worked on then? So it's looking like all you added to that one in your code was this bounces, or yeah. So you can add stuff to your code via that too. But does everybody have this right here? Excuse me, saved and everything? Just our bounce code. We all good on that? Alright, so here's where we get to some new stuff, I think. So I don't want you to make you do that now. You should have saved it already. So what we're going to start with today is by writing down this code exactly as you see it here. So this code is very similar to one of the first codes that we wrote, which is when we just, drew a line. But there's a couple extra things that we're doing. We are declaring a couple of different variables, x1, y1, x2, and y2. And we will declare the initial values for these variables as well. So in the void setup loop, we're declaring x1 to initially be 10, y1 10, x2 is 800, and y2 is 10. Within our void draw loop, we're adding something which will increase the thickness of our line. It's the stroke weight command. And we're substituting these variables, x1, y1, x2, and y2, into our line. And this is going to be a new program, yeah. Hence why I didn't really want you to open up a new, any program, since we are starting a new one. So you do need to write this down. I haven't written this down on my version of programming quite yet. So go ahead and get started on it, and I'll send the total code in a chat in just a moment here. Make sure that you do have your caps correct, especially in stroke weight. The W in weight is capitalized. So let me make sure this works before. Okay. I did send you this code in the chat, but you are welcome to write it by hand if you'd like. I know not everyone's a extremely fast typer, so. I would like for you to raise your hand once you've gotten this written down. And go ahead and run it as well, just to see what's just to see what it's doing. Nothing too crazy yet. The question is, does it have to be 1000 by 1000? Make it at least, for the y value, make the y value at least 800. Basically, if you do want to downsize it at all, you'll have to change some other parts of your code to do it, which is okay, but I'm not going to personalize it for you. I do have 9 other people here. So if you want to make it smaller, just make sure that you resize, or that you declare different integers, specifically where this 800 is. So if you want to do 500, make x2 400, but otherwise keep it as it is. It's not going to be fun. Liam's right. It's just a boring old line on a boring old background right now. In fact, real quick, I'll go right back to the code. It's just going to look like this. If you kept the original size. It'll look different depending on if you didn't choose the size you see here. Yeah, that's all it was. Your computer's not glitching or anything. That's exactly what you should be seeing. I mean, all we're doing here says syntax error on the x1 equals 10. Because your code looks right. Hang on, let's see here. You're making sure that it's within the void setup loop, right? So yeah, Gavin, let's look. That looks right. Yeah, you fixed it. All right. So it should look some boring line like this. Does anyone still need to see the code? Are we good? Oh, your code's not right. Okay, let me see a little bit closer. It's because you forgot a semicolon after stroke weight. So make sure you get these semicolons in, y'all. Make sure everything is capitalized correctly. This stuff's real finicky. It reads exactly what you put in there. If something's not right, it doesn't know what to do. Computers are dumb. So I'll go back to this code if you need, but you should see this. Now, using nothing but the line, how long do you think it would take to do this? So don't write this down, everybody. Well, technically, yeah, you could do it really, really quickly if you know what's up. But don't write this, y'all. We can sit there and do the line command a million times and only get this far. See, that's a lot of work just for that. Like, what if we wanted to get all of this? Would we want to sit there and type this individually for every single one? Yeah, we really don't want to do that. And we're going to introduce a new concept at this point called it's not a, well, hang on, there's 2 different people saying that. We're going to do what's called a finite loop. So remember we talked about the void draw being an infinite loop, meaning that it goes on forever or until you stop the code. We're going to talk about a finite loop, which in this case is going to be called a for loop, but I'll get into that in just a second. So programmers are really lazy. So what we like to do is, if there's a repetitive task, we like to automate it somehow. So here's a good example of it. Writing a script does take a while, but if you're doing something repetitive enough that it's like mind-numbing, it might be a good idea to write a script. So just consider this and understand why we're doing for loops, or these finite loops. So like I was saying, we're going to talk about for loops. The for loop is a little bit tricky, and it has broken many an aspiring programmer, including me. But once you get some experience with it, it'll make a lot more sense. So I had a horrible, horrible time with finite loops back in my Fortran class. It's why I never aspired any farther to be a programmer than that. So let's talk about it. Not Fortran, it's called Fortran, Fortran. It's an ancient, and by ancient I mean it was invented in the 50s, programming language. It's horrible and I hate it, and I wish that we never had to use it anymore. And this was actually the programming language that your parents and grandparents would program via punch cards. Like, they wouldn't code it, they would have physical pieces of paper and punch out holes in it and feed it into the computer. So that's how old Fortran is. I hate Fortran so much. So what I'm going to show you, and so Gavin is bringing up binary. We'll talk about binary a little bit later. I cannot read binary that is that long, so I don't really know if you're actually saying anything of meaning. I'm not very good at binary, but I'll try to give you a good explanation later. Anyways, so what I want you to do is take out the line, and I want you to type literally this, what you see here. It's gonna look weird, just write it, exactly as you see. The guy who made these slides likes to make funny names for variables, so yes, type in taco. It doesn't matter what the variable's called, as long as you can remember it. But in this case, it's gonna be taco. You're going to be typing this underneath stroke weight. You'll be deleting the line and type it underneath the line. Or sorry, and type this underneath stroke weight. And you can name yours Taco Cat. You can literally name it whatever you want to. I think in one of the next presentations he uses like potato or something like that. But I was just saying to name it Taco just to make it easier for you to follow along. Go ahead and run it and see what you see. Yours doesn't work. Go ahead and send me your code real quick. taco will exist if you declare it as an integer in this first part here. Jean-Marc, do you have the extra closed semicolon underneath your for loop? Oh, also, you forgot to add the extra taco right here before less than 500. Yeah. It does work now? Okay. Alright, so let's run some more Gavin's code to see what's going on, just for fun. Oh, okay. You just changed the size and renamed it as Super Taco Cat. But alright. So here's what's happening and how and why it works. So I wrote this in as the best out as I could. So the for loop has 3 arguments. So you can see there's 2 semicolons separating 3 different arguments here. So this first argument is going to contain an integer that we'll be using as an increment operator. So what we're doing in this code here is we're declaring a new integer, or a new variable called taco. So remember, this int declares an integer, and we're setting the initial value of it to be 0. Okay? So it's the integer to be used as an increment operator. The second argument here is going to be basically how many times the code should run before terminating. So if you all remember, the void draw loop is an infinite loop. It's going to go on and on forever until we stop it. But this for loop is actually requiring a condition to make the loop stop. So this for loop is going to run less than 500 times. The 499th time it runs will be the last time that it runs. Alright, so the last argument is by how much the integer should increase for each loop iteration. So if you remember the x++ we worked with last class, all we're doing here is replacing that x with the integer that we just declared called taco. So what this is doing is, for when we have an integer starting at 0, we are going to draw a line. Send me your code, Liam. We're going to be drawing a line going up by 1 each time, because we determined how much it's going to go up by 1, or right here in the third argument, which is just 1. It's going to do this 499 times until taco is at its maximum level, in which case the for loop is going to stop. So let me take a look real quick at Liam's number. Void setup, x1, 10, x2. You forgot to add the 4, Liam. The 4 before int taco. And you also forgot to write the taco less than 500. You forgot to add the word taco less than 500. So don't forget to put the 4 and put the taco. No worries. Alright, so what would happen if we increase this number to 800? What's going to happen to our GUI? What's it going to look like? You've never heard the word taco this many times within 5 minutes. Yeah. So it goes. Well, over 9,000, I mean, I guess you could, but it would just look like a black screen. But basically, what it's going to do is keep writing lines until it hits 799, and then it's going to stop. So if we have a look at what mine looks like now, Let's have it run instead 800 times. The block is just going to be bigger. Okay, so for loops take an integer, tell you by how much to increase the integer per loop, and when to terminate your loop. That's what all this is doing. So how can we make this? It looks very similar to what we just did, but there's it kind of hurts to look at actually. So I'm going to go to the next slide instead. How do we go about doing this? Not magic. Did you not see? Magic is not an acceptable answer. Duct tape also wouldn't work in this case. Duct tape only fixes mechanical problems. So what I want you all to do, we're doing two things here. The first is we're going to make the stroke weight smaller. Right now we have it at what, 13? Let's make it 7 instead to make our lines thinner. We're also going to replace this taco plus with taco equals taco plus 36. Everything else is going to be the same. So if y'all remember from above, when we did x equals x plus speed, we're doing the same thing here by taking the old value of taco and adding 36 to create the new value of taco. So it's going to keep doing that over and over and over again. Let's go ahead and dwell on that real quick. Do we have any questions on what we're doing here? You don't understand how it works? Well, the good news is I only hardly understand how it works, but let me try to explain it again. So we have 3 different conditions on our for loop. The first condition is just going to be any integer that you want. You can name it whatever you want, but we want it to start at 0. So the very first time that this loop runs, it's going to say, okay, there is some integer that we're using just for this loop alone, and it's going to start at 0. So it reads this before it goes into the for loop, before the loop even starts at all. It's going to run what's inside of your brackets here, however many times that you tell it to. We're telling it to run so many times until it reaches a number that's less than 1,000 in this case. So what's going to happen is it's going to run 999 times over and over and over and over and over again, all while creating new values of taco. So each time this runs, we're going to have a different value of taco. If the value of taco happens to go over 1,000, we're going to kick out of the loop. So yours is saying an error. Go ahead and send me your code real quick then. This last condition is going to be the increment operator, meaning that, okay, well, we're going to be increasing the value of taco by 36 each time we run this code. So I'm not saying this stuff is easy at all. It killed me in Fortran. It absolutely did. I had no idea what was happening. That's why I'm a mechanical-based person and not so much Fortran-based. So, Andrew, do you want to send me your code real quick so I can see what's going on with your error? So what it's saying, starting at 0, this is going to run in increments of 36 until it reaches 1,000. Yeah, the double plus is just basically shortening taco equals taco plus 1. The double plus is just shorthand for it. If you're trying to figure out how to paste it, select it all, Control C, and then Control V in a question. So specifically what this taco operator is doing, other than serving as an increment operator, we're also replacing this value of taco, replacing the y coordinate value with whatever our increment operator is. So what's happening is as as taco gets bigger, our y value gets bigger, which basically means that, let me get back to this one actually, basically means that we're going to draw lines lower and lower each time. So let's see what's up with yours. Andrew, you got to do, for the third argument, it has to be taco equals taco plus 36. And I know that it's not very intuitive, Tim, because I have some serious issues trying to explain it, as you can see. This is one of those things that'll make or break a programmer, unfortunately. So that's why we're putting taco inside the lines, just because, yeah. So let me take a look at what Sam had really quick. Let's see what's going on. Let me delete these guys. And yes, you can change the color of your lines, as well as your background, of course, but that is possible. So let me see what question we had down here. Oh my goodness, I have so many people setting so many things right now. Hang on. I'm trying to figure out what's wrong with your code here. I'm not seeing anything. Oh, it's because you don't have an an integer called x. You have x1 and x2, but you don't have just plain x. That's to you, Gavin. You don't have just plain x integer. You need to declare it, and then you can use that x. So just a second here, I'm going to conduct a poll to see how my pacing is today. I'm noticing that... Oh, I'm confused. Well, anyways, I'm going to see how my pacing's doing today. Just take a look-ski here. So I do have some more advanced programmers in here than I do in my later class. So I do have some too slows. And I do apologize. I literally can only go so fast, but you know, I will try to speed up just a little bit, especially because we are hitting lesson 3 here, and the first little bit of this lesson actually is about how computers work. I've been looking at this presentation earlier, and it's kind of all over the place. And there's some stuff I have no idea where his thought process was coming from. So let's see what's going on here. So essentially, computers at its very, very basic level is just an electric circuit. So here's an example of an electric circuit. We have a power source. We have, some electronic. And for it to be a circuit, we need it to be a complete circuit. So we need something going into out of the positive terminal and into the negative terminal. Now, if you've worked with electronics before, this circuit's a little bit misleading. Anybody worked with electronics that knows what we would need for this circuit? If not, it's okay. This is not an electronics thing right now. But yeah, John Mark's got it. You do need a resistor for this, but if you're not familiar with electronics, don't worry. I've burned many an LED out by not having a resistor to resist the current. So, Gavin, you broke what? Your code again? Send it to me. It's funny. Does it work at all, or is it just... Let's see what's going on with this code real quick. It's because you have a negative 1000 size, which doesn't make any sense. It's got to be a positive value for your width. Oh, okay. I thought you were seriously had no idea what was going on. So, the reason that computers have become such a big deal is because of what we call transistors, or the vacuum tube. What you see here are vacuum tubes. They're the same sort of principle here. You can find vacuum tubes in old school TVs. But basically what both vacuum tubes and transistors do is sort of control the flow of electric current. So, as you can see here, an iPhone has 32 billion of these guys. Transistors getting smaller and smaller by the day. Pretty wild stuff going on in that field. Now, if any of you are familiar with the Fallout universe, the reason that the computers are always so, old school is because the transistor was not invented until the late 20th century in that universe. So that's why the computers all look so old school in Fallout. That's why their history diverged from us, basically. But transistors are what's gotten our computers to where we are today. So if you'll notice here, transistors do have 3 pins. I'm specifically talking about Fallout 4, but New Vegas and 3 both have those old school terminals. So notice that these transistors have 3 pins coming out of it. They're called collector, base, and emitter. So what's going to happen is electricity is always going to be flowing into the collector, but it can't flow out of the emitter until something happens with the base. Specifically, what's going to be happening with the base, it's going to receive a signal, which is just some electricity. Electricity cannot flow all the way through a transistor until it receives an electric current from the base. From there, both the electric flow from the collector and from the base is allowed to exit through the emitter. So I'll expand more on what this has to do with anything in a second. Nowadays, no big deal, but back in the day, we had to have a physical person turning a physical switch to turn a switch, basically. That's not a very good explanation. But back in the day, we had physical people. Now we just have these nice transistors. And eventually, it led to the advent of logic gates, which are, I'm still not the most versed in these either. But don't worry. Basically, if you add some logic gates together and some wires, you get almost all the electronics you see around. And the guy who wrote this had no idea what this is, but it looked cool. Wires everywhere. Fun stuff. But the logic gates that he's talking about are in the form of what we call integrated circuit chips. They do crazy stuff in a circuit, just based on which pin you're activating. It's a very basic explanation there, crazy stuff. So we're going to switch over, and talk about binary now. So let's talk a quick joke. Only 10 types of people in the world, those who understand binary and those who don't. Now I read that wrong, there's no good way to read this out loud, as I just realized. But in binary, the numbers 1 and 0 correspond to the number 2. So binary is just it's a number-based system, which in our world is normally based on tens. So we have, 10, 100, 1,000, just adding zeros to the end of our stuff will increase the magnitude. But binary acts a little bit differently. So quick things, binary existed before computers did. It was invented by Gottfried Wilhelm Leibniz in 1646, and mathematicians are kind of weird, hence why they decided to do this. And you're not going to need to know binary. We're talking about this because we're talking about switches, which is what we're going to be working with next in processing. But basically how it works, what would correspond with the tens place? Y'all are familiar with numbers, you have the ones and the tens. Oh gosh, this is not an easy way to explain this at all. Basically what you'll notice is that if you square the number 2, you'll get 4. If you square the number 4, you'll get 16. That's how computers are based off of. Computers don't read in tens. They read in 2s. I'm really not good at explaining how binary works. Binary is one of those things that's just like, whoa, to me. But what you'll notice is that starting at 0, the binary for 0 is 0. The binary for 1 is 1, but the binary for 2 is going to be 1, 0. So notice that this 1 is going to the second place, which is basically the tens place in our language. Basically, don't worry about what this stuff means. All you need to know is that computers are all 1s and 0s. And before I get to that, Leibniz also did some crazy stuff to help us figure out calculus. I'm guessing base 2 has something very important to calculus. But let's talk about some more switch stuff. So again, binary is just 0s and 1s. 0 for off, 1 for on. So when you start stringing a whole bunch of binary together, you can make computers understand more and more complex things just using these 1s and 0s. So this is going to be the number 13 here. Computers can read this is 13 by seeing that the sequence of on, off, on, they'll understand that it's 13. So, here's where it gets kind of weird in terms of what he's doing here. He's talking about RGB and showing the secondary colors of it, so that's magenta, cyan, and yellow. But how computers read this is just based on binary. I don't know what's happening here, hence why I'm not explaining more about it. But basically we use RGB because it can go over 16 million colors. We can write English in binary and in numbers. I don't really know what his thought process was here when he's making this. But basically, computers at this very basic level are just 1s and 0s, turning switches on and off. The more quickly we can do it and the more small the transistors are that do it, the smaller our devices can get. Hence why old school computers were enormous, and now we can have all the stuff that an old school computer has in our in our pocket any time. So you just have to think about this happening trillions of times over and over and over again. So as you can see, this slide is very bizarre. I don't really know what's happening. So if you take a whole bunch of transistors, there would be a picture of a transistor here. Inside of your CPU, this is how we get everything to work. CPU being a processing unit is how our computer basically thinks. So go ahead and save what you worked on last time, or what you worked on a little bit earlier, which was save it as for loop. And we're going to go ahead and open up a new sketch. And we're going to write what you see here down. If you want to, you can make the size a little bit smaller. And you can change the background color, but keep the stroke the same. I'm going to put your hands down. Please raise your hand once you've gotten this written. We're starting to talk about user input here. And you can run it if you've written it down. It's going to look weird, but it's exactly what should be happening. And make sure that you do mouse over it some. What do you see? Lines that go where the mouse is. A black hole, the meaning of life. What you'll notice is that the X and Y position of your mouse is going to be one endpoint of a line that is centered at 500, 500. So one of the line endpoints is going to be the very center of your screen. It will be if you have size 1000, 1000. But at the center of your screen, it's going to be one end of your line. Your mouse, X and Y position, will be the other end of your line. So no matter where you go, it's going to keep drawing black lines. The stroke here is what defines the color of your line. I believe this would normally be in hexadecimal if you want to do a color that's not black. But I think that's some pretty cool stuff ultimately. Oops. Any questions just on that? I'm going to pause just for a second to see if we can actually get very... That's just explaining what all this stuff does. I already explained about the endpoint and wherever the mouse is pointing. Let's see here. See where the actual material gets back to. So, some people asking questions. We do want you to struggle a little bit because life is hard. I don't know why there's a random slide about the Centennial light, which is a very, 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 very old light bulb. Burning for 113 years. I wish I had that, so I never had to think about it. Changing light bulbs. But it's pretty impressive that ancient technology like that, ancient by like 100 years, could still actually go this far. So if we take... sorry, give me 1 second to take a look at what we're looking at here. I guess we have time to do that. Yeah, let's go ahead and add in our void draw loop a couple of prints. So what's going to be happening when we add these prints, it's going to tell us our live X and Y position of our mice. And it's going to print them in the console. So let's go ahead and add that so you can actually see the relative position of your mouse. And the question is, why don't they make all light bulbs like that? Because it's probably really expensive to make light bulbs like that. Expense is pretty much everything there. Because they want to keep selling light bulbs. It's called planned obsolescence. They want things to break after a certain amount of time so that you'll buy more. But yeah, so go ahead and write exactly what you see here, taking note of what are strings and what are not strings. So the first and third prints will require strings here. Okay, yeah, that's where we're going to end then. So you'll notice that the console is not part of your GUI, it's not part of your game or anything, but it is handy to have stuff written in the console so that you can bug test your code, for example. So all it's doing is printing mouse X equals in the console, putting the live mouse position, as well as printing its Y position at where it presently is. I'm not going to go any farther than that because we're going to start doing some more functions beyond today. But while I still have you here, there is the makeup lab for the Charlotte Saturday labs on Saturday. It's at 10 a.m. We do not have webinar on Monday. We will have it on Wednesday, though. So it'll be another week before I see you again. If you've gotten all this written down, I want you to save as, let's just save it as mouse, and you're good to go. So we will have a webinar on Wednesday. We will not have it on Monday. I'd probably do it in a different code than your for loop. I'd probably make your own sketch here, or your own new program here. But once you've gotten it and saved it, you are free to go for the day. Yeah, definitely. So let's see what this code here has got for us. We got pretty far today, though, actually. I'm kind of surprised. Not in a bad way, of course. Definitely in a good way. There you get some crazy stuff done. And that is a seizure for the eyes. But feel free to ask questions or